Hello and welcome to my channel. In this tutorial, I'm going to show you how to model a reinforced concrete two-dimensional frame using ETABS 2015 software. So let's take this frame for example. It consists of three bays. The span of each beam is 4 meters from center to center of the column, and the height of each floor is 3.4 meters. The load is applied on each beam with a value of 25 kilonewtons per meter, plus the own weight of the structure. So the beams have their own weight, the columns have their own weight, and they should be included in the analysis. So let's start. We will go to ETABS. We will start a new model by clicking at this icon here. We will go to use built-in settings because this is the first time we are using the software and it's the first time to make this model. However, if we have previous models, then we can use settings from a model file. In this case, we will have the same sections defined in that file. We will have the same units. We will have the same materials and the same everything that we spend time in defining. So it would be a better option to use this one. Or you can make your own template, and in this case you will use saved user default settings. But for now we are starting from scratch, so we are using the built-in settings. We will use the metric SI units, which is Newton, meter, and centigrades. Of course, the metric MKS is meter, kilograms, and second. So it's just like the kilograms instead of Newton. In the US, customary, as you know, it's like the feet, the pounds, and the Fahrenheit. So we'll go for the metric SI unit because I'm more familiar with it. We are not designing steel, so we don't need these two for now. For concrete design code, if we want to design our frame, then you can choose the code relevant to your country. For example, in Canada, I'm going to choose the CSA 813.3-14, which is the new code, and click on OK. Now the program is asking us about our grid system. So the grid system is basically just like a sketch of horizontal and vertical lines that assist us in drawing the frame later. So it's like when we were back in school, we have those copybooks of for mathematics, for trigonometry, where we have like intersections. Here in this program, it allows us to draw our own default intersection. So in this PowerPoint file here, we have the sketch of the frame. And here the program is asking us about the number of grid lines in the X direction. So the X direction is this way here. The Y direction is out of plane, so it's inside the screen. And this is the Z direction. It's upward along the frame. So in the X direction, we have 1, then nothing. Then we have 2, then nothing. 3, then nothing here, and 4. So we have 4 changes, like 4 columns, 1, 2, 3, and 4. Therefore, we need 4 grid lines in the X direction. In the Y direction, we don't have anything because we are modeling a 2D frame, so we'll put 1. The spacing grid in the X direction, as you can see here, it's a typical value. It's 4 meters. In case it was not typical, then you can write the most repeated value here, and then go to the grid labels and adjust the other values. Spacing grid in Y direction is not important, so we can leave it because we don't have any other repetition in the Y direction. Regarding the height of the building or the Z direction, we need to provide the value in terms of the number of stories. Here we have nothing, ground floor, then story 1, story 2, and story 3. So we have 3 stories. The typical story height starts from here to upward, stroke 3.4, and the bottom story height from the foundation level to the first floor, so it's 3.4 as well. We will choose the grid only in this case and click on OK. We will have 2 windows. The first one will show you the plan view, the other one will show you a 3D view. Now we are not interested in the 3D view because we have a 2D model, so we'll just close the window. And here we will click on elevation because we are interested in seeing the elevation of the building. A, B, C, and D will show you the um, the frame from its side. We are not interested in that. We want to see it from its elevation view, showing all the columns and beams. So we'll click on one and we'll see it from its front view. So this is the grid system. They are just lines that assist us in drawing. Now, the first step after getting the correct grid system is to go to define material properties. Here we will define the materials that we are going to use. We are analyzing reinforced concrete, so we have concrete and steel bars. So we need to define both materials. Here we have default materials already defined for us, but we are going to define our own materials. Let's say that it's United States and concrete, and the standard is user so that we can define our own material. Here in the material name, write any name that you want, which will remind you with the material. Let's say that this is concrete with 35 megapascal. The material is concrete. Isotropic, because the concrete has the same properties in all directions. You can change the material color if you like, and modify show notes if you want to write something to remind you with this material. The weight per unit volume of concrete, it's usually 23 to 25, so I'll keep the default. Modulus of elasticity, I like to take it as 4,500 times square root of fc prime, which is 35. Of course, the program has a built-in calculator, so I just wrote the equation and then tab to go here. I'll keep these, then modify and show the property design data. Here, this is the important thing. We need to write at 35 megapascal and okay, just to match the name. Like this, what will make the difference in terms of strength. And this is what will make the difference in terms of elasticity. So these two numbers are very important when analyzing or designing the frame. If you have a nonlinear material data, so if you want to analyze or model the frame based on the actual material properties, you can go to these boxes, but for now they are not important. We are just going to analyze the frame based on elastic analysis. So let's now add another material, which is the steel, to define the steel bars. So let's write any name that describe this material. So let's say steel with a yield strength of 400 megapascal. As again, it's steel. Of course, you can write rebar as well, but steel is more general. It's also isotropic. And modulus of elasticity, I like to take it as 200,000 megapascals. These are okay. Modify show properties. We have to change this. So minimum yield strength is 400 because this is the material we are defining. The minimum tensile strength, it depends on the plastic hardening plateau. So it's usually 500 or 550. It depends. So you can leave it as is, or you can just change it. It's not very critical because we are analyzing the section based on elastic analysis. So the 200,000 megapascal is governing here. If you have a nonlinear material data, so if you want to enter the complete stress strain curve for steel, you can do that here, but it's not important in this case. It may be more important if you are doing nonlinear analysis, or if you are doing some research about the actual behavior of the structure. So now we have defined these two materials, the concrete and the steel. Click on OK. We have our own materials ready. Now we need to define the sections. Here we are defining frame sections, a 2D frame section. So we are defining frame sections. We don't have any slab or any other thing. We just have frames. Now here we have some built-in sections, like DW sections and steel sections and so on. But we are going to define our own sections here. So you will go to define section property, frame section. So add new property. Here we have like many options to choose from. So let's say that we have, like here you can choose like anything from here, like let's say steel T, steel angle, anything you like, and then press OK. But here, like these are the frequently used shapes, so you just click on the shape itself rather than choosing from here and then go to OK. So you have two ways. For concrete, we are going to use the concrete rectangular section, so I can click here directly, or I can go to concrete rectangular, then OK. Let's define the beams as, let's say, beam that has a width of 200 millimeters and a height of 350 millimeters, and they are made of concrete 35 megapascal, and it's concrete rectangular, and the depth is 350 and the width is 200. Now for the reinforcement, go to modify show rebar. This is a beam. If you want to adjust these values, then you can do that here, like the cover to the longitudinal rebar, you can do it here. If you have some area override, you can do that here, but I'll keep it as is now. And modify, show the modifiers. Usually the sections are cracked in real structures, and the modifier would be a value of 0.35 of the actual inertia for beams when considering the moment of inertia, I mean, and it's 0.7 for columns. This is according to the Canadian codes. And this is the section properties. You can get the area, the inertia, the radius of gyration, anything you want. And then, okay. Let's add a new property. Now we are going to define the columns. They are rectangular sections as well. So we'll say column. And let's say that they have cross-section dimensions of 400 by 400 millimeters. And they are made of concrete 35. So here we have 400 by 400. Go to the property modifier, so the moment of inertia will be adjusted. So this would be 0.7 and 0.7. You can adjust the weight if you want to reduce it, and the mass and so on, the cross-sectional area. We don't need to do that here. For the reinforcement, this is column, rectangular, ties, choose steel as reinforcement, steel 400 megapascal. You can adjust these values as well if you like, but keep it as default for now. And okay. Of course, you can define other beams and you can define other columns. And let's take an example. Let's define another column dimensions. Let's say column 300 by 300, and show modifiers 7.7, and of course if you have like a tower or a bridge or something, then you will have many columns and beams. So you will define in this step many columns and beams, and you'll spend some time here, and you'll get a list of all the columns and beams. Just be consistent. So if you write, let's say for naming, beam 200 by 350, this means that 200 is the width and 350 is the depth or the height of the cross section. Keep it consistent so that when you choose the section later, it would be easy for you. Now, we chose the material, we defined the material, we defined the section. Now let's define the load pattern. We said that we have a dead load, a superimposed dead load, plus the own weight of the structure. So here, this problem, we don't have any live load, so we'll say delete load. The own weight is here, let's say modify load. So the own weight, its type is dead, and the self-weight multiplier is 1. This means that we are considering the weight of the structure or of each member, the weight of each member, to be considered as 1 times its weight. So we are considering its weight. If we put this value as 0, this means that we are ignoring the own weight of the structure. Let's add now the superimposed part. So let's write anything here. Let's say superimposed dead load, and its type is super dead, and the self-weight multiplier is 0 as shown here. Add new load. So this is the own weight. So this number is 1 times the weight of each member, and superimposed dead load, this means that this is 0 times the self-weight of each member, which is 0, plus the superimposed dead load. We'll see that later. And press OK. Now, here you will go to load combinations and add a new combo. In this case, we have a load combination of 1.4 dead load. So this is dead load. We are adding it linearly, so like algebraic addition. So we'll add the STL. So this is 1.4 dead and 1.4 STL. Because the dead load is composed of 2 parts, the own weight of the structure multiplied by the factor, and the superimposed dead load of the structure acting on the structure multiplied by the scale factor, and then we go and press OK. Of course, we can have many other loading cases here. You can click here and get the code recommendations for you, like you'll get the loading factors automatically. You'll just need to go and make sure that they are correct, or you can add them one by one by clicking here. If you have, for example, live load, so we'll have 1.2 dead plus 1.5 live, and so on. Now let's draw. ETABS makes it very easy to draw the frame members. You'll just need to click on this icon here, select the type that you are drawing. So here let's start with drawing the beams. We have this beam. Just click on each grid line and you will see that the beam is automatically drawn. Done. Now, let's go and draw the columns. Here we have two columns. Let's say that the 400 by 400 columns are placed in the ground floor, and the other columns, the 300 by 300, are in the first floor and second floor. That's it. The frame is ready. Now, regarding the supports, we have many options. We can uh, consider them as pin supports, or we can consider them as fixed supports, as you can see here. In this case, the supports will resist the moment plus vertical loads plus horizontal loads, and this is a conservative assumptions as a conservative assumption that will give you more moments on the structure, on the columns here. Sorry, it will give you more moments on the foundation. And if you want to model the supports as pins or pin supports, so let's say here go, and this is pin. So you are limiting the translation in X, Y, and Z directions. And here you will get more forces or more straining actions inside the members of the frame, but you will have lower loads on the foundations. In reality, the actual case is something in between. It requires some engineering sense and some engineering judgment, a discussion with the team. It depends the um, numbers that you get from the soil reports provided to you as a structural engineer. You can model the supports here instead of pins and fixed supports. You can model them as spring supports, like from here. But it needs some calculations. There are many references found in literature on how to model the supports, but usually the pins are okay. Now let's assign the loads on the beams. So select them, then go to assign, frame loads, distributed, and we said that the on weight is already included, so we have to define the superimposed dead load, and because it's applied uniformly, so we just write its value here. It's 25. So as you can see here, we have 25 uniformly distributed loads. If we have like other kind of load distribution, we can just write the loads here, like this load corresponds to a point allocation of 0 of each beam. This is 0 of this beam, and this is the 0 of this beam, and this is the 0 of this beam, and 0.25, which is here, 0.75, which is here, 1, which is here, and similarly for all beams. Replace the existing loads, so if there are previous loads defined on these beams, they will be removed. And okay. So this is the frame after the load is applied. We have everything ready, so let's click on run. Okay, we need to define, so let's say this is tutorial 1 and save. Now this is the deformed shape of the frame due to the applied loads. If you want to see it, start this. Now if you just highlight, or if you just like hover with your mouse over any joint, so you can see the translation in the X, Y, and Z directions in millimeters. As you can see here. Of course, inside the beam here, we don't have any joints defined, therefore we can't get the actual values, but I will show you a trick later on how to get these values. but you can get the values of the deformations now on the nodes. Now to see the straining actions here, let's say we want to see the axial force due to the load combinations 1.4 dead with the values. Click OK. Here are the axial force distribution acting on the columns, the beams, if any. If you want to see the shear force acting on the structure, here it is. So this is the shear force distribution. You can get these values and make sure if your structure is safe or not. If we want to see the moment, click on moment 3, and here it is. This is the bending moment diagram acting on each beam. These are continuous beams. So here it is. You can zoom in, zoom out, and click on each beam and then right click and you will see the actual values. It's quite easy and useful. If you want to design your frame and make sure that it's safe, go to design, concrete frame design, and click on start design. Check. Then design concrete frame, verify analysis, verify check analysis and design match for all concrete frames. So this means that the frame is good. A concrete frame. Okay. So sorry, I repeated the procedure for all members because in the first time I selected this one by mistake. Okay, then design concrete frame and go to verify all members passed, all concrete frame passed design check. So all of them are safe. And this is the area of steel and we are good. So I wanted to show you like the procedure of getting the deformations here in the beams. What we need to do is to select the beams again, go to edit, and then edit frames, divide frames, and let's say that we'll divide each beam into 5 different objects and click on OK. In this case, you will have many joints inside each beam. Run the analysis, and here you are. You have a joint here where you can see the deformation. You have another joint here where you can see the deformation, and so on. I hope this tutorial was helpful for you. Like it's my first tutorial to do on YouTube, so I'm still practicing on how to uh, talk and do the work at the same time. So I hope like you learn something or like if you have any concerns, if you have any questions, any comments, anything, just please write them in the comment boxes. If you like my channel, then please subscribe. I'm planning to upload other videos in the future. And that's it. Thank you for watching the channel. Bye for now.